طيب إن شاء الله تستمتعوا بهذه المحاضرة and let's get started.
Hello everyone, my name's Dr. Simon Foster. I'm a solar physicist at Imperial College in London. I'm also a member of the Imperial Space Lab. My research looks at changes in the sun and how they could impact the Earth. Now today's talk I'm going to talk about the sun, and it's called Our Living Sun because, believe it or not, our sun hasn't always been here. It was born. It will actually live a varied and changing life, and one day it will actually die. And it's these changes that it's just like a human being in this way. It's these changes that mark its life, and we're going to look at these different changes, and we're about halfway through its life at the moment. So let me get started. So here we are. Now this here is a picture of the sun, but it's actually taken in X-rays. So the sun doesn't just emit visible light, it emits different frequencies of light, all the way from radio and microwaves all the way up to X-rays and gamma rays. And looking at the sun through different frequencies, through different types of light, we can see different features, and that's really important for solar physicists like myself. Now the sun hasn't always been here, okay? Before the sun, in this region of space, there was other stars. There was at least 2, possibly 3 other stars, and these were first generation stars. These were the first stars created after the Big Bang. Now these stars were huge, and they burnt through their fuel really, really quickly. And what happened was, because they were so huge, they exploded in something, you may have heard of it, called a supernova. And one of these stars would have exploded and ripped apart the other stars nearby. Now in doing so, it scattered debris over, wow, hundreds of light years, okay? All this debris would have been scattered out there. Now over millions of years, this debris would have started to come together. It would have started to coalesce. Now at the centre, hydrogen and helium would have started to come together. Slowly it would have gathered more and more under its own gravity, collecting more and more material in, until eventually the sun was born. Now in the material around it, you would have got the debris, the leftover material. And it's a bit like a builder's yard. Whenever you get a building and you made a house or anything, there's always material left over. And it was a bit like this with the sun. There was material left over from these other stars, and they formed the planets. Now, it's a bit like if you rub your hands together, you know, they get warmer and warmer and warmer. These planets, these early worlds, would have been really hot and lava-filled, okay? And the sun would have been really hot just from the friction. Now, what would eventually happen is that material, the hydrogen and the helium at the centre of the solar system, this new solar system, would have got hotter and hotter and denser and denser and denser, and eventually it would have ignited. And it was a bit like a baby letting out a scream. It would have let out a colossal roar, an explosion, and it would have affected all this dust and debris and early planets around it. Now I'm going to ask you a question. Is it easier to blow a rock or a piece of dust? Just think about that. Well, it's easier if I had a rock here and a piece of dust here. It's easier to blow the piece of dust, and that's actually pretty similar to what happened in the solar system. So you had all this leftover debris, and when the sun kind of roared into life, all the light material would have got blown further out, and all the rocky, heavy material would have stayed close to the sun. And this is why we have the rocky planets close to the sun, Mercury, Venus, Earth, Mars, and then you have the gas giants further out, Jupiter, Saturn. Okay, so that's how the sun and the solar system was born. And this is what it looks like now. Okay, so this is our sun. You can see there's lots of different features on it. There's some kind of what we call like flares or prominences coming out of the edge. There was bright parts, dark parts. I should point out, please do not look directly at the sun. This is taken through a special telescope in space. But there are lots of features on its surface. However, what's powering the sun? So, if we look at this, it's actually hydrogen. It's a type of nuclear energy called nuclear fusion. Now, you may have heard of nuclear power. Okay, there's two different types. There's nuclear fusion and nuclear fission. Now, fission is big. It's like elements such as uranium and plutonium, big, heavy elements that are too big to hold themselves together, and they break apart into smaller elements and let out a small amount of energy. Now, the opposite is true here. This is called nuclear fusion. And fusion, if you fuse something together, is you stick something together. Okay, so here in nuclear fusion, what you're starting with is 4 hydrogen atoms, okay, or nuclei, protons effectively, and you're squashing them together. Okay, and as you squash them together, 4 protons squash together and they become a helium nucleus, and that's 2 protons and 2 neutrons. Bizarrely, 2 of the protons turn into neutrons, and that I find that absolutely amazing. Now, here's a simplified version. Okay, you've got 4 protons going in, squashed together, boom, out comes helium, and a small amount of energy is also released. But how do we know this? Well, it's thanks to this chap here. Can any of you figure out who this is from just this picture? Have a look and see if you can figure it out. Okay, some of you, okay, 1 or 2 of you may have got this. Let's move on. I suspect quite a few of you got it now, if you look at the eyes, and I suspect you all know who it is now. This is Albert Einstein, and he had his famous equation E equals mc squared. Now, what does this mean? Well, actually, what it means is the energy and mass, the stuff that you're made of and everything is made of, is interchangeable. You can turn energy into mass and mass into energy. It's mind-blowing. And because it's E equals mc squared, now the c stands for the speed of light, and that's squared. Okay, now the speed of light's a big number anyway, and squaring it, you get an absolutely huge number. What this means is, from just a small amount of mass, you can generate a huge amount of energy. So, in the sun, 600 million tons of hydrogen is fused every second. Okay? Now, 0.7% of that just disappears. It gets turned straight into energy, and that's because a neutron is ever so slightly lighter than a proton. Okay, so bizarrely, 4 million tons of hydrogen, 4 million tons, is just disappearing every second. It's becoming energy. And to give you an idea how much energy that's releasing, that's equivalent, if you were to fuse that much, to about 90 billion tons of TNT. That's how much energy the sun, our star, is releasing every second. Now, why is that so important to us down here on Earth? Well, imagine you had a snowflake in your hand. Just put that snowflake out. Imagine you've got a tiny, tiny snowflake in your hand. Now, that's made of water, H2O. If you took the hydrogen from that snowflake and fused it, you would generate your entire lifetime's worth of energy. That's all the energy you need for your entire life from the hydrogen contained in just one snowflake. This is why everyone is so desperate to get hold of nuclear fusion. This is why it's such a technology and energy source that everyone's so desperate to discover or be able to make possible here on Earth. But actually, how do we know that the sun's made of hydrogen and helium? We can't go there. What we can do is look at the light. So you know, just by looking at a rainbow, that white light can be split into the colours of the rainbow, all the way from red at one end to violet at the other. I was trying to remember. Richard of York gave battle in vain. Red, orange, yellow, green, blue, indigo, violet. Okay, but actually, if you were to split white light from the sun up using a prism, you'll actually see that it isn't pure. Okay, there's little lines in it, and these lines are the fingerprints, the identifiers of the elements inside the sun. So actually, you may be familiar with this chap. This is Isaac Newton, and he was obsessed with looking at prisms and how actually what the makeup of light was. Okay, and so he was the first person not to split light with a prism, but recombine that split light back into white light. So he knew they were interchangeable. Now, why does this happen? Why are there these kind of black lines, these fingerprints in the light? Well, it's down to the atomic nature of atoms, of elements. Okay, so you may be familiar with the structure of the atom, and this is it here. You've got the positive nucleus where the protons and neutrons are, and orbiting around it in shells, you've got electrons. Okay, so what I've got a picture of here is hydrogen, one proton, one electron orbiting around. And you've got here the periodic table. Okay, and the periodic table just basically tells you how many protons and electrons and neutrons by the mass are in each element. Now going through, here are the kind of structures of some of the basic elements. You've got hydrogen, helium's got 2 electrons, lithium's got 3, beryllium's got 4. And it's these electrons orbiting around that actually give elements, I suppose the easiest way to say is their fingerprint. And every element in the periodic table, every element here, has got its own unique fingerprint. Okay, and this is how we identify elements, because if we pass electricity, energy, through a gas of hydrogen, actually these electrons get pushed up. They get much like if you throw a ball up, they go up to a higher energy shell, then fall back down. And when they fall back down, they give off a photon of light, of energy. And it's at very specific frequencies, okay, depending on the element, depending on the electron shells. Okay, and this is their fingerprint. So the one I've got here this is the fingerprint of hydrogen. Pass electricity through hydrogen gas, and you'll get these 4 different colours out. Okay, and in the UK, I don't know if in other countries, but we used to have what's called sodium street lights. Our lights actually had sodium gas in. When you passed electricity through it, they would give off orange, because actually orangey yellow was the predominant line in sodium. So this is what street lights in the UK all used to look like. They've changed a bit now, but when I was a kid, all street lights looked like this. And to give you an idea, this is what I find really interesting. Here is a gherkin. Now, gherkin is a pickle, okay, in the UK, and it's got salt in it, sodium and chlorine. So much salt, in fact, that if you pass electricity through it, and hopefully this is going to happen. That could be the fuse, right? When electricity, now don't do this at home, you've basically, these people have taken a gherkin, a pickle, put 2 nails into it and connected that up to an electricity supply. Please don't do that. But when you pass electricity through it, because it's so sodium, that sodium, the electrons get excited in it, go up, fall back down and give off photons of light, and you can see the orange there. Now what's also interesting is that if you pass normal photons, just pure light, through an element of a particular gas, it won't emit, but it will absorb in the same frequencies as it emits that. Okay, so if you try and pass energy through a gas of a particular element, those fingerprints, those frequencies where it's sensitive at, it will actually absorb lighting. So you can see here in this picture here, at the top here, I've got it here, this is where hydrogen absorbs, and it absorbs in the same frequency it emits in. So you can see this when you pass pure white light, photons, through a gas, say hydrogen, it will actually block the certain fingerprints, and this is how we use it to identify it. So in the sun, it absorbs those frequencies in its fingerprint, and so when it gets to come out and it hits towards the Earth, actually these fingerprints are there. There are black lines where it's absorbed the kind of frequencies of hydrogen and helium, and this is what it looks like. Hydrogen looks like this. Helium's on the right hand side. You can see it's slightly more complex. Now when we look at the sun, you can see there are absorption frequencies, lots of them. You can see them here. And when people first looked at this, actually they thought that actually there must be a mysterious element in the sun that was unique to the sun. Okay, they knew about hydrogen because hydrogen, you could blow it up. Chemistry is really about blowing things up. But there was something there that they didn't know, and it was helium. Helium's a noble gas. It doesn't react with anything. So they thought that helium was a special gas that was only found on the sun, and I believe they called it chromospherium because they thought it existed in the corona of the sun. Okay, so that's actually where, bizarrely, helium was actually discovered on the sun, not on Earth first. Now we can actually use this as well to look at other stars and other planets, because actually when, say you have a star and its light passes through the gas of a planet that goes in front between the Earth and the star, actually you can see what fingerprints, what elements are present in its gas. And this is how we know when we talk about exoplanets, planets orbiting around other stars, this is how we know what they're made of. So this is the structure of the sun, okay? So we've got the core, this is the centre where the fusion happens. Then around it you've got what's called the radiative zone, and this is where the material passes straight out, pushes straight out. And then you've got something called the convection zone. Now you may have heard about convection on Earth. Convection is where you have hot material rising, cold material falling. Hot material rising, cold material falling. And then this leads to the very edge of something called the photosphere, and this is the visible surface, and this is what I'm interested in. And above you get the chromosphere and the corona, which you can only really see in eclipses. Now, how do we actually see deep down into the sun? Well, we use something called helioseismology or seismology. You may have heard of this from earthquakes. Well, the sun kind of has waves travelling across it, actually. And the sun's surface can be thought of as a bit like a bowl of tomato soup. And this is actually what me and my old PhD supervisor used to call the surface of the sun. We called it the tomato soup because you may know about convection. Hot material rises, cold material falls. Hot rises, falls, rises, falls, rises, falls. Okay, and if we look at the surface of the sun, so this here is a satellite looking at the sun, okay, and it's focused really, really tightly in. And if I press on that, can you see, hopefully, you should be able to see there are dark patches and bright patches. Hot material rising in the bright patches, cooling down and falls back down. So you get, they're called cells. Okay, material. And this, if I've got it at the bottom, this is me recording here, me making some tomato soup, actually spaghetti, sauce, and you can see it's exactly the same. You've got the, I'll try and get it over here, hot material rising here, it's falling around it. Okay, so you've got hot material rising on the sun, and then it's falling, just like in a bowl of tomato soup. Now, on top of this tomato soup, we've got the things that I really love, and these are called sunspots. And these are big, dark, black patches on the sun's surface. And this is one here taken in 2007. Okay, now the tomato soup bubbling away is about 5,700 degrees Kelvin, but a sunspot is only 4,000 Kelvin, okay? It's nearly 2,000 degrees colder than the surrounding area. And if we have a look, if we have a close-up at a sunspot, you can see here, you can see the tomato soup bubbling away here, and this is a sunspot here, big, cold, dark black patch. And actually what's really interesting is that an average size sunspot is about the size of the Earth, and they appear in pairs. Okay, so you usually have them as a pair, which you can see here. And I think it looks a bit like, have you ever seen The Sunflowers by Van Gogh? It looks a bit like that to me. I think this is a beautiful image. By the way, this is me. I've superimposed this picture of the sun on. Okay, so this isn't, the Earth isn't really there, okay? But going back to the first picture I showed you, and the picture here of the in X-rays, you can see that these are what we call magnetic field line. Now the sun's a giant magnet. Like the Earth, it has a north and a south pole. But over the what we call a solar cycle, it breaks down, and actually these magnetic loops pop out in places where they shouldn't. They no longer appear at the north and south pole. They appear all over the surface of the sun. And this is where you get sunspots. So this is why you get them in pairs, because you've got the loop coming in and the loop going back into the sun. Okay. And what's really interesting is this is why you get sunspots, because you may know about from electromagnetics. So if you have a moving charge, it will produce a magnetic field, and a magnetic field will deflect a moving charge. Okay, so the sun's actually a charged gas. It's what we call a plasma. Okay, and it's a big soup of charged material. Okay, and obviously, therefore, if you have a big magnetic field near it, it's going to move some of that material around. So what's happening in the sunspot is where you have these really strong concentrated magnetic fields, it pushes the material out of the way. And it cools in these areas, and this is why sunspots appear cooler. To give you an idea, I've got an old TV here. Okay, this is an old cathode ray tube TV. And what I've got here is a magnet. So a cathode ray tube uses electrons to hit the screen, and the electrons are charged particles and they're moving. But if I introduce a magnetic field where there shouldn't be one, these electrons don't hit the screen where they should. They hit the screen where they shouldn't. And you suddenly get these strange patterns. And this is effectively what's happening on the surface of the sun. You get materials getting pushed away from where it should be to where it isn't, and you get cooling in those areas. Now, sunspots aren't new. They've been around for thousands of years, well, millions of years probably. And the first drawing of the sun was taken in 1128 through a forest fire in Britain by a monk called John of Worcester, and you can see it here. It must have been absolutely huge. And if you put it side by side with a picture taken from a satellite, as I say, you can see just how big that sunspot must have been. Now, Galileo also made drawings of sunspots. He actually pointed his telescope at the sun and then projected the image down onto a huge table, because obviously if you look for it, the sun through your eye, you can really do yourself damage. So he actually projected it onto a table and would draw the sunspots. Now what's really interesting is that it's possible, hopefully, I'm going to do this here, to actually, come on. Brilliant. It's possible to animate Galileo's observations of the sun, which I've got on the left here, and look at them with modern satellite observations, which you can see here. And can you see they're behaving the same? Now, this was about 300 years ago. No, 400 years ago, actually, that Galileo was doing this. This was in 1613 and 1614. So it was over 400 years ago. So we know for 400 years, sunspots are behaving exactly the same. And their numbers go up and down in what we call the solar cycle. Okay, and there was a period called the Maunder minimum, which you can see here, when they completely disappeared from the sun's surface. We don't know why. Really interesting. But when that happened, the Earth got really, really cold. There was a mini ice age. And in London, the River Thames would freeze over from November through to February, so much so that people were able to live on it. They held fairs on it. There was horse races, bonkers. So this doesn't quite make sense though, because if sunspots are cold, and when you have fewer of them, the sun gets colder. What's going on? And this is actually what my supervisor first said to me. He said, do you expect the sun to get hotter or colder when there's fewer sunspots? I thought, well, sunspots are cold, so when there's fewer of them, the sun should be hotter. It's actually the opposite. When there's more sunspots, the sun gets hotter, and this is peculiar. Now, if we take a closer look at the sunspot, here is a sunspot. As it travels across the surface of the sun, you can see the energy decreases, it dips. So what's going on? Well, actually, there's something else. And there's something, little bright features on the surface of the sun called faculae, and they outweigh the sunspots, okay? So even though they're very tiny and small, they outweigh the number of sunspots by about 10 to 1. So when you have more sunspots, you have more of these faculae, these torches, and weirdly the sun gets brighter. Here you can see a faculae going across the surface of the sun, and you can see here the energy goes up. So looking at this picture here with a filter on our camera, you can see that actually the sunspots are dark. These faculae, these torches, are brighter. They outweigh. So weirdly, there's more sunspots, there's more faculae, and the energy goes up. It is a good image of faculae in red. These are the warming of these bright little bits, and in blue you've got darkening. And actually, if you put them together, you see that over the solar cycle, you get more sunspots, and less sun's energy will increase when there's more sunspots, decrease when there's less. And actually, the sun's energy output is quite easy to calculate. It's easy to calculate. I can do it. And it's a very simple equation. And it tells us that solar radiance, which is sun's energy output, is a mixture, it's a combination of quite sun, which is the tomato. Is a good image of, you've got faculae in red. These are the warming of these bright little bits, and in blue you've got the darkening. And actually, if you add them together, you see that over the solar cycle, as you get more sunspots, then less. The sun's energy will increase when there's more sunspots, decrease when there's less. And actually, the sun's energy output is quite easy to calculate. So easy to calculate, I can do it. And it's a very simple equation, and it tells us that solar irradiance, which is the sun's energy output, is a mixture, is a combination of the quiet sun, which is the tomato soup bubbling away, sunspot index, the photometric sunspot index, which is simply the effect of sunspots, and the brightening of these faculae. Okay, and adding this together, we get this lovely image here. This is from a satellite, so this goes back till 1978. We can actually say it's gone up and down, up and down, up and down, but there's been very little difference in the past 40 years. However, if we model further back in time, this is what we see, and we see that actually in the past 300 years, the sun's energy is slowly gone up. Its energy output, it's got hotter and hotter, and this actually has impacted upon the Earth's climate. The Earth would be slightly warmer because the sun's got slightly more hotter, I suppose. However, the effect of carbon dioxide in the atmosphere is making this even worse. It's amplifying this effect. So what other factors are also on the sun? Well, there's these lovely things called solar flares. Now, here I've got a picture of one of these loops, these big magnetic field lines. And you can imagine their magnetic loops are a bit like rubber bands, okay? And what happens with a rubber band when you stretch it too much? It can snap. This is what we're going to see here, hopefully. So out the limb here, boom. This is what happens when you get a solar flare. Okay, these rubber bands are there. Occasionally they snap and they release tons of energy. It's called a coronal mass ejection. A lot of people use the word solar flare, and it launches it out into space. And what's really interesting is that you get more of these when there are more sunspots. So the amount of sunspots go up and down over what we call a solar cycle, which you can see here again. And when we're up here, more sunspots and more solar flares, less sunspots, less solar flares. Occasionally one of these can hit the Earth's magnetic field. What it does is when one of these flares hits the Earth, it pushes the magnetic field back and actually breaks it. And as it breaks the magnetic field lines, energy can feed down, and it feeds down at the poles, the North and the South Pole. And what we get is the aurora. So we get the aurora borealis at the North Pole, the aurora australis at the South Pole. And the different colours tell us different things. So red is oxygen, green is oxygen, blue is nitrogen, and reddy purple is nitrogen. So you've got a green one here, so this means that there's a lot, it's exciting the oxygen in the atmosphere. And we're back to talking about those fingerprints. Again, energy being dumped into a gas, it's making it excited, giving off light. What's really interesting is, well, dangerous is that if these things are actually quite bad for the Earth. So we've got satellites watching the Earth. One called LASCO is just ever so slightly further ahead and closer to the sun. So if a solar flare hits this satellite, we know 24 hours later that solar flare will hit the Earth. So this is like an early warning system. So what you're seeing here is data from that. So you can see here that one went over it, and there's a really big one in a second. Oh, by the way, there it is. Now it hits the LASCO satellite, and we know that in 24 hours that will also hit the Earth. Okay, it's an early warning system, so this tells us to be careful for satellites orbiting the Earth because they could be damaged, or power lines on the Earth could also be damaged. And there was one actually in 1859 called the Carrington Storm that was so powerful that it broke so many magnetic field lines, it pushed the aurora from the North and the South Pole all the way down to the equator, and it could be seen in the Caribbean, in Jamaica. And what's really interesting, there was a powerful solar storm last year, and this is a picture taken from Trinidad. And this is one of my students. His uncle lives in Trinidad, and this is a picture of the aurora taken in Trinidad. So there was such a powerful storm. It caused the aurora to be seen in Trinidad. And I've actually seen the aurora in England. I've seen it in London and a city called Bath in England. I've seen it a couple of times. You don't have to travel to the North and South Pole. So what does this mean for astronauts? Say if you want to go to the moon or Mars, what does this mean? Well, on Earth we're protected by a magnetic field. And actually on the space station, the International Space Station, you're also protected by the Earth's magnetic field. But in space you've got a bit of a problem. Now when the Apollo missions went up, you can see here they're in the grey lines, okay? And the blue sticks are when solar flares hit the Earth. Now you can see a couple of them got really close. Now the yellow ones, which actually might have hit Apollo 9, that's above annual dose. So that means you would have got your annual radiation dose in one go. The orange ones here means you increase your or at least doubling your risk of cancer over your lifetime. So the one with Apollo 13, which you can see here, that nearly hit, and that would have raised their cancer risk. Now this one here is severe radiation sickness. This is really bad. This is where your fingernails fall out, your hair will fall out, and you will be very, very, very ill. You'll probably survive it, but you'll have severe lifelong problems caused by it. However, if we look at this one here, this would have been instantly fatal. Now people at the time didn't know this. Okay, so they launched themselves and didn't know. And this is why it's such a problem going back to the moon and onto Mars, because if you get hit by one of these, really, really dangerous. Now, finally, what's next for the sun? We've seen it as a newborn, kind of as a teenager, it's got spots. What's going to happen now as an adult? Well, actually, when it runs out of hydrogen fuel, it's going to start burning helium, and it will get bigger and bigger. And it kind of, like adults do, as all men do, we get fatter. We get slightly redder. And this is what's going to happen to the sun. It will become what's called a red giant. And it will actually grow at least 10 times, possibly 100 times its size. And we believe our sun will actually swallow up the Earth. Now, after this, that will go on for a few billion years as a red giant, and then it will run out of fuel completely. Now, unlike bigger stars, it won't go supernova. It needs to be about 8 times bigger than our sun for it to go supernova. Instead, it will just shrink down and it will become a white dwarf. It will become a really hot, basically ember of a star. It won't fuse anymore. It could actually become a giant lump of coal, of carbon in space. And we know carbon under heat and pressure becomes diamonds. So our sun eventually could just become a huge diamond in space. But eventually it will get colder and colder and colder, smaller and smaller. Like all of us, my nan, you could imagine, actually I say she was a white dwarf because she got white hair and she getting smaller as she got older, as we all do. And that's what's going to happen to our sun. It. So thank you very much for listening. It's been a real pleasure, and I believe I will now be around to answer some questions.
طبعا هي كانت المحاضرة. شكرا لمتابعتكم. طبعا رح نبدأ هلا بالرد على أسئلتكم مع الدكتور سايمون. طبعا لو عندكم أسئلة فيكم على Q&A، فيكم تحت بالبوكس اللي مكتوب فيه أسئلة وأجوبة، فيكم تبعتوا الأسئلة عليه، وهلا رح نبدأ نجاوب على الأسئلة اللي وصلت. Thank you for watching. You can put your question in the Q&A box, and we'll be starting now Q&A session with Dr. Simon. Dr. Simon, thanks for being with us today.
Hello, everyone. Hi, thanks for having me. It's wonderful being here with you.
Well, we're pleased to have you here, and we will start with the first question. So the first question is, how big is the sun? I'll address the question in Arabic and get back to you to get the answer. طيب الدكتور سايمون كان طبعا برحب فيكم وعم بيقول انه هو كمان مسرور بانه ينضم لنا. السؤال الاول كان سؤال بسيط عنا. اول سؤال انه قديش كبيره الشمس؟ قديش هو حجم الشمس؟ Back to you, Dr. Simon.
Okay, this is a really good question, and it's actually got several different parts, because when we think of big, there's different ways of interpreting that.
All right. السؤال عم هو في الحقيقة سؤال مهم، وسؤال في له أجوبة، في له عدة أجوبة. راح نجاوب عليه بعدة طرق.
So when we think of size, we can think of radius, and that's how the distance from the center to the edge of the planet. And the sun is about 100 times bigger. The radius is 100 times that of the Earth. So the Earth has a radius of 6,500 kilometers, and the sun's radius is about 700,000 kilometers.
Right. فلو نحكي مثلا عن نصف القطر مثل ما بتعرفوا هو المسافة بين المركز والسطح. فالنصف قطر الشمس أكبر ب100 مرة من نصف قطر الأرض. نصف قطر الأرض حوالي 6500 كيلومتر، بينما نصف قطر الشمس 700,000 كيلومتر. Back to you.
Thank you.
Simon.
Thank you, Nazeer. But if we look at volume, that's like if you inflate a balloon or a ball, how much space it takes up. 1,000,000 Earths could fit inside the volume of the sun. And that tells you how big it is. That one of the those sunspots on the sun's surface is the size of the Earth. So that's the takeaway. 1,000,000 Earths could fit inside the sun.
Interesting. إذا بدنا نحكي عن حجم كحجم، هلا قلنا نحن نصف القطر إنه هو 100 مرة، ولكن كحجم حجم الشمس هو مليون مرة حجم الأرض. يعني الشمس بتسع مليون أرض. حجم البقعة اللي البقعة السوداء الصغيرة اللي بتكون على الشمس هي بتكون بحجم الأرض.
And just to finish this off, the sun is so big that if you look at the solar system, so that's the sun and all the planets and the asteroids and meteorites and comets, 99.8% of all the mass of the solar system is in the sun.
Right. كمان اذا نحن يعني مشان نتخيل قديش هي كبيره الشمس، فالشمس بالنسبه للمجموعه الشمسيه، المجموعه الشمسيه بما فيها الشمس والكواكب والمذنبات والكويكبات، فحجم الشمس من المجموعه الشمسيه حوالي 99.8% من حجم المجموعه الشمسيه. يعني الأرض وبقية الكواكب والمذنبات كلها بتشكل هذا القسم الصغير اللي هو 0.2%، والشمس 99.8% من حجم المجموعة الشمسية. Right, so that was for the first question, right? So the second question is how hot is the sun? Also, I'll say the question in Arabic and get back to you. سؤالنا الثاني هو قديش درجة حرارة الشمس أو قديش سخونة الشمس، قديش هي سخنة. Back to you, Dr. Simon.
Thank you. So this again has three parts to it because it depends on where you look at where the how you describe the hot is, if that makes sense. So there's different parts to the there's different answers to the question.
فهذا كمان السؤال يعني في عدة أجوبة عليه، أو بدنا نحدد وين عم نحكي، بأي منطقة أو بأي جزء من الشمس. ففي عنا عدة أجوبة لهذا السؤال. Back to you, Dr. Simon.
Thank you. So if we look at the core, the center of the sun, where this nuclear fusion is taking part, the sun is 15 million degrees Celsius. So that's incredibly hot. It's one of the hottest places in the universe.
فلو نحكي عن المركز، عن نواة الشمس، جوا الشمس النواة، محل ما عم بيصير الانصهار النووي، فهون درجة الحرارة هي 15 مليون درجة مئوية. You, Dr. Simon.
Thank you. However, if we look at the tomato soup, which is the area, the surface that we can see with satellites, the area that I'm interested in, that's around 6,000 degrees Celsius. So it was very hot, but it's like being near a fire. The further you get from the fire, the more spread out that energy becomes. So on the tomato soup, it's about 6,000 degrees.
فلو نحكي عن مثل ما سماه الدكتور بالمحاضرة حسائل الطماطم أو اللي هو سطح الشمس، فسطح الشمس بيكون أبرد من داخل الشمس. الفكرة مثل لما بيكون عندنا نار، كل ما بعدنا عن النار كل ما بتخف الحرارة. فدرجة الحرارة على سطح الشمس بتكون 6000 درجة مئوية، بينما بتكون 15 مليون جوا الشمس في الداخل بالسنتر، بس السطح بيكون حوالي 6000 درجة مئوية. دكتور سايمون.
Now, finally, there's a really, really interesting and kind of puzzling part to this answer, because the sun has a gassy outer atmosphere that you can see during an eclipse. It's called the corona, and this is like the gas surrounding the earth, and that is 1,000,000 degrees, and we don't know why, because the further you get from the fire, the cooler it should become. But for some reason, this gas is really super hot, and we don't know why. And it still puzzles scientists, and it's the big question we have about our sun.
Alright. هلا نحن قلنا انه جوعا بتكون درجه حراره 15 مليون، بعدنا لما وصلنا للسطح صارت درجه الحراره 6000، ولكن بعد السطح في منطقه الكورونا او منطقه التاج او منطقه الهالي، بنسميها الهالي. هي المنطقه اللي هي تقريبا مثل الغلاف الجوي تبع الارض، مثل غاز المحيط بالارض. بهي المنطقه في عنا بيكون درجة الحرارة عم بتكون حوالي 1,000,000 درجة. فالمفروض انه نحن عم نبعد عن مركز الشمس، المفروض هون الحرارة تكون اقل، يعني كانت 15 مليون صارت 6000، المفروض تنزل وتصير اقل على بعد السطح بمنطقة الهالي. ولكن لسبب لحد الان ما بنعرفه، ولسبب لحد الان هو معضلة علمية، انه ليش عم بتكون درجة الحرارة عند الهالي حوالي 1,000,000 درجة مئوية. Right, so I think that was the whole part of the answer,
Yes.
right?
Yeah, that's answered, hopefully.
All right, thank you. So we'll go to the next question. How often does the sun's magnetic field flip?
Another really great question. Sorry, I'll let you answer it and say that in Arabic.
Okay,
Sorry.
yeah, no problem. Yeah, I'll say the question in Arabic first. طبعا في عندنا لون سؤال انه كم مره او يعني قديش بيصير هذا التغير بالحقل المغناطيسي للشمس. طبعا مثل ما بتعرفوا حكى الدكتور بالمحاضره عن الحقل المغناطيسي، كيف بيكون في قطبين للحقل المغناطيسي، فقديش بيتغيروا هدول القطبين. وطبعا الدكتور سايمون علق سؤال، سؤال فعلا مثير. Back to you, Dr. Simon.
Thank you. Sorry about that. I get very excited.
No, it's fine. Yeah.
The sun's magnetic field flips. Well, there's different ways of seeing it. It flips every 11 years. So if you've got north at the top and south at the bottom, it flips in 11 years, and you have south at the top and north at the bottom. Then 11 years later, it flips again, and you're back to north and the south. So there's two ways of looking at it. You can either say every 11 years or every 22 years for a complete cycle.
Right. فالجواب هون انه الحقل المغناطيسي للشمس طبعا بيكون في البدايه، مثلا لو كان احد طرفي الشمس هو القطب الشمالي والطرف من تحت مثلا كان القطب الجنوبي، بعد 11 سنه بينقلب هذا الحقل وبيصير فوق الجنوبي وتحت الشمالي، وبعد 11 سنه ثانيه بيرجع بينقلب. فطبعا فينا نفكر فيها كانه كل 11 سنه بنقلبه، او كانه كل 22 سنه بتصير دوره لهذا الحقل المغناطيسي. Right.
But there's one final answer I should say to this. Occasionally, we can look in records from here on Earth. We can see that occasionally the sun doesn't flip for maybe 300 years or even 1,000 years. It stops flipping. And again, this is another puzzle, and we don't know why.
So it's sometimes it stops flipping and sometimes it gets back to flipping.
Yes, it's so we saw this in that thing called the Maunder minimum in my talk, that just after Galileo made his observations, for 100 years there were no sunspots, and we believe from records on Earth, from gases in the atmosphere that tell us about this, that the sun's magnetic field didn't flip for 100 years, and we can see lots of times in history.
اوكي. طبعا بس كنهايه للجواب على السؤال نفسه، انه احيانا عم بتوقف هذا الانقلاب بالحقل المغناطيسي الشمسي عم بيوقف. فمثل ما حكينا بالمحاضره، بالفتره اللي ما كان في بقعه شمسيه فيها، فبهي الفتره ما تم انقلاب لل... للحقل المغناطيسي للشمس. فليش؟ طبعا ما بنعرف امتى بيوقف. ف ولكن انه احيانا بيعدي عده سنوات، ممكن 100 سنه بيعدي وما بيصير انقلاب للحقل المغناطيسي، ولكن لما بيكون بالشكل الطبيعي كل 11 سنه بينقلب الحقل المغناطيسي. So I think that was it, Dr. Simon, right?
Yes, thank you.
All right, thank you too. So we'll go to the next question. How do we know how old the sun is?
Oh, sorry. Do you got to say that in
Yeah,
Arabic?
yeah,
So,
thank you. السؤال إنه كيف نحن عم نعرف عمر الشمس؟ Back to you, Dr. Simon.
again, this is a very good question. So what we look at is something called ratios. So we believe that when the sun first started, it was all hydrogen and there was no helium. But we know that the helium is formed when hydrogen is fused together, when it squashes together. Now, at this time now, the sun has a different ratio. There is lots of helium. I'll answer more. Sorry, if we go to there.
اوكي alright. هلا نحن كيف بنعرف؟ هلا نحن يعني عم نطلع، نحن بنعرف اول شيء انه بداية الشمس بالهيدروجين. الهيليوم الموجود هو الهيليوم الناتج عن تفاعل الهيدروجين، عن الانصهار النووي اللي عم يصير بالهيدروجين. طبعا نحن عم نطلع على النسبة بين الهيدروجين والهيليوم. Back to you, Dr. Simon.
Thank you. So when the sun was born, there was no helium, all hydrogen. Now, when we use special instruments to look at the sun, we can see that the sun is now 75% hydrogen and 25% helium. And if we know how the rate at which that helium is being created, we can calculate how old the sun is. We can kind of go back in time and work out how long all that helium took to be created. So that tells us, it gives us a guess of how old the sun must be. And there's also another reason I can give as well.
Oh, good. Well, that's very good and smart idea to know, right? right. الطريقة اللي عم بيقول نحن نعرف فيها إنه الشمس بديت بهيدروجين 100%. هلا نحن من خلال طبعا التسجيلات اللي عندنا بنقدر نحدد قديش نسبة الهيدروجين البقيانة في الشمس وقديش نسبة الهيليوم اللي تشكلت في الشمس. حاليا نحن لما بنطلع على الشمس بنلاقي انه 75% منها هيدروجين، 25% منها عم بيكون هيليوم. فهلا نحن لو عرفنا سرعه تشكل الهيليوم، نحن طبعا نعرف سرعه تشكل الهيليوم، فاعتمادا على سرعه تشكل الهيليوم، طبعا الهيليوم كان صفر في البدايه وهلا صار 25%. فاعتمادا على سرعه تشكله نقدر نحسب الزمن اللي بدي او اللي نعم اللي بدي الهيليوم يتشكل فيه. من خلال هالشيء بنقدر نعرف عمر الشمس. وعم بيقول طبعا الدكتور سامي انه في شيء ثاني كمان رح يقولنا عليه كمان بيدل على العمر. Okay, so another thing also that indicates how old the sun is, right? Okay.
Yes, that is, we can use our own planet, we can use Earth, and we look at the rocks on Earth, and we know that the Earth is about 4.5 billion years old. And from our understanding of how the solar system was formed, we kind of believed that the sun would be about 500 million years older than the Earth. So we take 4.5 billion years as the age of the Earth, add 500 million, and we come up with 5 billion. So that's another way we can work it out.
So we get the same answer. So we right in
Yes.
both ways.
Yes.
Yeah.
Hopefully, but it reinforces it. It makes us, it shows us we've got two different ways of coming up with the same answer. So hopefully the answer is correct.
So yeah, this is what I mean. Yeah, well, good.
Fingers crossed.
الطريقة الثانية انه نحن فينا نطلع على عمر الارض طبعا من خلال الصخور الموجودة على الارض. ففينا نعرف انه عمر الارض 4 مليارات سنة ونص. كمان من خلال نظرياتنا لطريقة تشكل المجموعة الشمسية فينا نقول إنه الشمس تشكلت قبل نص مليار سنة من الأرض تقريبا. فإذا نحن قدرنا من الأرض نعرف إنه عمر الأرض هو 4 ملايين ونص سنة، فمعناتها بنقدر إنه عمر الشمس 5 مليارات سنة. طبعا سألت الدكتور انه نحن طبعا حصلنا على نفس الجواب بالطريقه هي او بالطريقه القبلى، وبالتالي هذا بيدل على انه نظرياتنا او انه عم نمشي بالطريقه الصح. وطبعا كان جواب الدكتور انه نعم فعلا نحن سواء باستخدام معدل او سرعه تشكل الهيليوم او باستخدام عمر الارض قدرنا نحصل على نفس الجواب لعمر الشمس. So I think that was it. Want to add anything to that?
Yeah, no, that's that answer. Yes.
The answer. Well, thanks. Well, yeah, we'll go to the other question. Can we create a sun, maybe a smaller one on Earth? Okay, I say the question here. السؤال هون انه نحن فينا نعمل شمس صغيرة على الأرض. Back to you, Dr. Simon.
Short answer, yes. And
Wow.
believe it or not, it has been done several times on Earth already. And I'll explain a bit more in a second, but I'll go to them.
Alright. طبعا عم بيقول كإجابة صغيرة نعم فينا. وهذا الشيء الحقيقة صار على الأرض. نعم نحن عملنا هذا الشيء على الأرض ورح يشرح لنا هلا الدكتور. Back to you, Dr. Simon.
So, as I explained in my talk, this type of power is called nuclear fusion. And on Earth, we do actually have people who've created reactors, nuclear reactors called fusion reactors. And they take huge amounts of hydrogen and have really strong magnets to contain it, heat it up to huge temperatures, and you do that hydrogen squashes together, makes helium and releases lots of energy, just like on the sun. But we've only managed to get this to happen for a couple of seconds.
All right. So our sun was like has an age like that is way shorter than the real sun, right?
Yes, it's happened like that.
I see. طيب فاللي قدرنا نعمله نحن الحياة على الأرض إنه قدرنا نجيب ذرات هيدروجين نحطهم بمجال مغناطيسي نعطيهم الطاقة لحتى يصطدموا ببعضهم ونعمل الانصهار النووي أو الالتحام النووي. إنه هدول الهيدروجينات اصطدموا في بعضهم عملوا الهيليوم. ولكن فهذا طبعا مثل شمس مصغرة صار هون، يعني نفس العملية اللي عم تتم على الشمس صارت هون. ولكن نحن لحد الآن ما نجحنا بأنه غير بأنه نعمل هي العملية لمدة ثواني، يعني ما دامت الشيء ما أنه صار عندنا تفاعل يطول مثل التفاعل بالشمس. Alright, add anything to that?
No, just to say that I work with people that there is a reactor in Britain that tries this, and so there are people, scientists all over the world trying to get these to create a star that will last a long time and create lots of energy.
Well, good luck with that. Give us updated with the results.
I should always say it is always 10 years in the future. And it's always 10 years in the future. So 10 years ago, nuclear fusion would happen in 10 years' time. Now we're 10 years in the future. It's going to happen 10 years in the future. It's always just out of reach.
Okay, well, good luck with it. Right. So عم بيقول دكتور انه هو الحقيقه هلا حاليا عم يشتغل مع ناس ببريطانيا على على انه يحاولوا يعملوا نجم بحيث يطول شوي، يعني يكون بفتره اطول. طبعا عم نقول له انه يعني ان شاء الله بتوفقوا بهذا الشيء. عم بيقول حاليا انه هن عم يعملوا لسه تجارب على هذا الشيء، وعم يحاولوا يعني يتعاونوا مع عده باحثين في العالم لحتى يقدروا يوصلوا لنجم او يعني شمس مصنوعه بحيث تطول اكثر. Right, so we can go to the next question, right?
Yes.
So I have maybe interesting question here. Um, are we expecting, or like, can we expect mini ice age, like a sun with no dark spots in the future? Yeah, I'll say the question in Arabic first. Yeah. All right. السؤال عندنا سؤال هون انه هل فينا نتوقع العصر الجليدي الصغير؟ اذا شفتوا بالمحاضره حكى الدكتور عن انه صار مثل عصر جليدي صغير وقت صارت الشمس بدون ثقوب او بدون بقع مظلمه، وقت صارت الشمس بدون بقع مظلمه وصار الجو على الكره الارضيه بارد جدا. هل فينا نتوقع هالشيء؟ هل فينا نعرف ايمت ممكن يصير بالمستقبل، او هل ممكن يصير مره ثانيه؟ So back to you, Dr. Simon.
Hopefully, yes. But it is very, very hard to predict when. The sun is so old that for it, this 11 years is like a heartbeat for a human being. And so trying to predict when this will happen is very, very hard.
So yes, we can expect it, but like
we don't know when. Yes.
So it is gonna happen, but we don't know when.
It will happen. There are these little 11-year up and downs. And then there are very long 1,000-year and 10,000-year ups and downs. But trying to find the evidence of those, and these very long ups and downs, what causes our ice ages. But because trying to gather the evidence, we've only got a few thousand years. Does that make sense? So trying to predict it is very, very hard, but it will happen.
Right. طبعا نحن عم بيقول الدكتور انه لسه من الصعب علينا الحقيقه انه نعرف امتى بالضبط. طبعا عم بيقول انه اكيد رح يصير، لانه هي بتصير كل دوره، يعني في دورات شمسيه، يعني مثل ما في عندنا دورات ال 11 سنه بيقلب فيها الحقل المغناطيسي تبع الشمس، وعم بيقول 11 سنه بالنسبه للشمس هي مثل دقه القلب بالنسبه للانسان، طبعا باعتبار شو عمر الشمس الكبير. التوقع انه ايمتى راح يصير في عندنا شمس بدون بقعه شمسيه وبالتالي راح يصير عندنا عصر جليدي، اكيد نحن بنعرف انه هذا الشيء راح يصير، ولكن امتى لسه من الصعب انه نعرف، لانه هي الدوره بالنسبه لنا عم تكون بطيئه، يعني ممكن هي عم تصير كل 10,000 سنه، كل 1000 سنه، كل يعني في عدد كبير من السنوات عم حتى تتكرر هي الدوره، دورات لما بيزداد فيهم البقع السوداء وبينقصوا، فمن الصعب انه نعرف بالضبط ايمتى، فلحد الان لسه ما فينا نقدر تماما. Anything to add to this?
Yes. So just over 100 years ago, there was a mini ice age on Earth. It got very cold, caused by the sun, because there were very few sunspots. Now, it is my hope and the hope of lots of scientists that maybe we would get one of these mini ice ages very soon, because the temperature on Earth is going up and up and up because we're adding more carbon dioxide. So if we get a mini ice age, strangely, the Earth's temperature won't plunge. It will actually, instead of carrying on up, it will plateau and will go straight up. So the carbon dioxide in the atmosphere that's causing global warming will actually act like a blanket, and actually basically where the Earth's temperature should be going down, it will make it stay normal. So this is actually my hope that could help us, protect us from the worst aspects of global warming.
اوكي جود. فطبعا عم بيقول الدكتور انه هو طبعا صار ال ال من 100 سنه تقريبا صار هذا الشيء. وايضا sorry doctor, that was 100 years ago, right?
Yes,
You
it
said
was
that I
about
said
1900, 1880 to about 1900. Yes.
right. فهذا الشيء صار يعني باخر 1800، من اكثر من 100 سنه، وعم نتوقع انه يرجع يصير قريبا. والدكتور زي عم بيقول انه يعني العلماء بيأمنوا انه يصير هذا الشيء قريبا، لانه حاليا درجه حراره الارض عم ترتفع بسبب غاز ثاني اكسيد الكربون السي. فلما عم يرتفع لما عم يصير هذا الاحتباس الحراري في الارض، فوجود لما بده يجي بقى يصير عندنا هذا العصر الجليدي، هذا بيخفف طبعا السي او 2. عم بيقول راح يشتغل مثل غطاء بيحمي الارض، يعني فبيخفف من حده الاثار، وايضا بيخفف الاحتباس الحراري على الارض. Right, I think so. That was it, right?
Yes. Yeah.
Yeah, well, I think we need to finish here. I think our time is over. So I want to thank you a lot for joining us today for this interesting information.
Can I just say shukran to everyone. Thank you very much, Nazeer, as well, because you translated my words.
Of course,
And
yeah.
I know that I've got a very strong, hard London accent, so hard my wife
It's
doesn't
good. It's good.
understand me at times. So thank you very much for
Of course, you're more than
understanding
welcome.
me and making me sound wonderful in Arabic.
Welcome. All right. So as our time today is coming to an end, I would like to thank all for participating in our lecture event. Thank you, Dr. Simon, for answering us the question. And if you have any further questions or question wasn't answered today, please post your questions at our Instagram page. You can see the details on the screen. And of course, the Phoenix team will address all of them.
I think I might be doing an additional video, yes, or to answer the questions.
Yeah. Of course, we'll do that also too. And after the lecture is finished, you will get a small survey from Zoom. So please take just like 1 or 2 minutes to fill it out. So because we really would love to know your opinion. See you at our next lecture. طبعا بنهاية الجلسة بنحب نشكركم كلكم على المشاركة، بنشكر الدكتور سايمون. إذا في عندكم أسئلة، سواء أسئلة قدرتوا سواء الأسئلة بعتوها ما قدرنا نجاوب عليها أو لسه ما بعتوها، يا ريت تبعتوا لنا إياهم على صفحتنا على الانستغرام. شوفوا الصفحة هون على الشاشة قدامكم، فبعتوا لنا الأسئلة على الصفحة. فريق فينيكس راح يجاوبكم عليها، وأيضا الدكتور سايمون راح يعمل فيديو وينزل الأجوبة لأسئلتكم. فطبعا راح نحاول نجاوب على كل الأسئلة اللي بعد. طبعا عزيزونا اليوم الوقت ضيق فما قدرنا نجاوب على كل الأسئلة. شكرا كثير لحضوركم. طبعا بعد نهاية المحاضرة في هلا بس طلعتوا من الزوم فورا الزوم راح يعطيكم استبيان. هذا الاستبيان صغير، يا ريت بس تحاولوا تعبوه لأنه حابين نسمع رأي. بنشوفكم بالمحاضرة الجاية. Thanks everyone.